All right, so let's talk about a couple of reactions we can do after we've done an electrophilic aromatic substitution. So these are all reactions that do not take place on the aromatic ring itself, but rather take place on a alkyl side chain that we've added before, or some other type of side chain that can be reacted. So most of these reactions we're going to talk about will occur at what's called the alpha carbon. We've dealt with alpha carbons before. The alpha carbon is the one that's attached to the interesting part of the molecule. So if we have an aromatic ring here, the alpha carbon is the carbon that's directly attached to the ring. It's not a member of the six-membered benzene ring. It's the first carbon on the alkyl side chain. So the alpha carbon is more reactive than other carbons in the chain for a lot of reasons. First of all, because it is in conjugation with the double bonds in the ring there. So any kind of reactive intermediate we have on that alpha carbon, whether it's a carbocation or a radical or an anion, that can be spread throughout the ring by resonance. Let's start by talking about oxidation of those compounds. If we react some sort of aromatic alkane like this, or an alkyl benzene, let's call it like that. This is butyl benzene. If I react that with a strong oxidizing agent, like potassium permanganate, along with water, has to be aqueous, the alpha carbon can be fully oxidized. So when a carbon is oxidized to its greatest oxidation state, that means it has as many carbon-oxygen bonds that are possible on that carbon. So all of the hydrogens get replaced, any further carbons along the chain get removed. And what we're left with is a carboxylic acid functional group, C double bond O, OH, right there on that same alpha carbon that we talked about. So we're just left with one carbon now attached to the bond. It has C double bond O, OH as a functional group. So we can make pretty much any alkyl benzene into a benzoic acid in pretty decent yield with potassium permanganate. One restriction that we have on this is that we need at least one alpha hydrogen. Alpha hydrogens are, as you'd guess, the hydrogens that are attached to the alpha carbon. So anything attached to the alpha carbon are also called alpha. So we need at least one alpha hydrogen. So when I have tert-butyl benzene, I have a quaternary carbon with 3 methyl groups that's attached to the ring. No alpha hydrogens on that carbon, so oxidation is not able to take place. The reason for that is that an intermediate to this is a radical on the alpha carbon, okay, with however many H's are attached to that. But if we have 3 CH3 groups, we cannot abstract a hydrogen. Sort of the first step of this is abstracting one of those alpha hydrogens to get the radical there. So let's just call that an intermediate. The actual mechanism for this has several steps, and it's pretty complicated, so we don't need to worry about that. But what we do need to know, potassium permanganate, KMnO4, with water will oxidize an alpha carbon all the way up to a carboxylic acid. So if we ever need to make benzoic acid, or if we need a C double bond OH group on an aromatic ring, that can come from any alkyl group, which we then oxidize. Another form of oxidation, which actually has a similar mechanism to what I just talked about, is bromination. Back in chapter 10, we talked about how if I have a double bond, the allylic carbon can be brominated. That's the carbon that's next to, not a part of, but next to a double bond. So we use N-bromosuccinimide, NBS, as a source of bromine that's generated in situ. So if I have any kind of alkyl benzene, as long as it has at least one alpha hydrogen, one of those alpha hydrogens will be replaced by a bromine. So we have a bromine here. This is 1 bromopropyl benzene. So I have a 3-carbon alkyl group attached to the benzene, but a bromine on the first carbon attached. NBS, it's really a source of Br2, but it allows us to form that bromine radical which performs this reaction. So these are the two propagation steps. So if you need to look back at radical reactions from chapter 10, there are two propagation steps for every radical reaction. The first step will involve abstraction of a hydrogen. So, and remember, I'm drawing these single-headed arrows because it's one electron. So one electron from the CH bond will meet the one electron from the Br dot. This is a bromine radical. The other electron will land on the carbon, giving us this benzylic radical, which is resonance stabilized. The radical character will be spread out through the ring at the 2, 4, and 6 positions. The benzylic radical then will be able to react with a Br2, okay, allowing one bromine to become attached to that alpha position, regenerating the bromine radical to go on and continue reaction. One useful application of this that we've talked about and we see in the textbook is that if I have an alpha brominated benzene, like this 1-bromoethyl benzene, if I react that with a strong base, like hydroxide, what's going to happen here is that the hydroxide will attack one of the beta hydrogens. Remember, bromine is on an alpha carbon. These are beta hydrogens on the carbon next to it. Hydroxide will attack one of the beta hydrogens. Right there. The electrons from the CH bond will go in to create a double bond, and then the carbon-bromine electrons will go on to the bromine, which will kick the bromine off of the molecule. So we will do an E2 elimination, leaving us with a compound like this. This is styrene, benzene ring with a CC double bond attached to it as a substituent outside of the ring there. So remember, E2 reaction happens in a single step where the hydrogen is attacked, simultaneously the double bond is formed, as well as the bromine, or the leaving group, being kicked off. So if we ever need to synthesize something with a double bond right outside of the ring in conjugation with the rest of the benzene double bonds, we can do it by elimination of an alpha brominated benzene.